Thanks so much to the organizers. This has been a wonderful conference. I'm so happy to be here. Yeah, so let me just, we'll just situate everything. On Thursday, I think we're going to talk about reionization. Yesterday, we had a great discussion about black hole formation. Today, I think, is mainly a lot about questions about the assembly of galaxies and the cycling of gas through galaxies and the way stars are formed. And so one of the ways that we have of trying to answer questions about the way that gas cycles through galaxies is by looking at what we call galaxy scaling relations. So in particular, one of the ones that people in my group like to study is what we call the mass-metallicity relationships. The variation in metal content in galaxies as a function of galaxy mass is one of these ways that we have of probing the inflows and outflows of gas in galaxies. And in particular, there's some really starkly different predictions from simulations for how this scaling of metallicity versus mass evolves with redshift. So this is just showing the predicted evolution in oxygen abundance for a 10 to the 8 solar mass galaxy as you go back in time. And you can see, different simulations have wildly different predictions for what this oxygen abundance should be at earlier times. So if we can actually make this measurement beyond redshift 4, we can get some really interesting constraints on feedback models and galaxy formation and other really interesting stuff. So what's the connection with JWST? Well, of course, one of the ways we have of probing the oxygen abundance in galaxies is by measuring nebular emission lines from star-forming regions. And so in the past, I would always give a talk and show like a crappy Keck spectrum of a redshift 2 galaxy. Well, this is our JWST NIRSpec spectrum of a redshift 2.5 galaxy that hosts the detection of 50 emission lines. And I'm highlighting in purple the emission lines, the strong emission lines that we would typically use in the past with our Keck studies of redshift 2 to 3 galaxies to constrain the oxygen abundance of galaxies just based on translating ratios of strong emission lines into the physical quantity, the oxygen abundance. So one of the messages is that we can do better now. JWST definitely gave the promise of being able to measure the mass-metallicity relationship and its cousin, the fundamental metallicity relationship, out to early times, and a lot of us were really excited about that. And so there was some early work led first by Nakajima et al., measuring the mass-metallicity relationship between redshift 4 and 10. This is a recent compilation from a few weeks ago by Sarkar et al., showing combining the public data sets like the Sears survey and the JADE survey, showing oxygen abundance versus stellar mass between redshift 4 and 10, even breaking it up into different redshift bins, so 4 to 6, 6 to 8, and 8 to 10. The evolution is mild. It's consistent with some simulations, not others. You require some feedback that doesn't remove too many metals or accretion that doesn't cause too much dilution. But hopefully what you can see is that as you get between redshift 6 and 10, there just aren't that many galaxies. So clearly we need a larger sample. The same thing goes for the fundamental metallicity relationship that looks at the combination of mass, metallicity, and star formation. So this is a connection that seems to be invariant in galaxies out to redshift 3, but then it actually, in this nice paper by Kurti et al., shows that as you go beyond redshift 6, galaxies seem to have lower metallicities for a given mass and star formation rate as you get to these early times, suggesting that the equilibrium is not in place at the earliest times. Again, this is wonderful, but the sample is too small to really see what's going on. Okay, so these are great early stabs at establishing this scaling relation, I think it represents an initial attempt. So we've heard a lot about bursty star formation histories. My student Leonardo Clark tried to look at this from a different angle from the one that Dan was talking about, which is basically looking at what we call the main sequence of galaxy formation, star formation rate versus stellar mass in different bins of redshift using a combined public data set from Sears and JADES. Okay, so the angle here, so our particular angle is to construct this relationship of star formation rate versus stellar mass using different indicators. The H alpha star formation rate, which is sensitive to fluctuations on short timescales, looks like this. This is the main sequence when you use the UV star formation rate. So hopefully what you can see is that there's a lot more scatter in the H alpha main sequence, H alpha, UV, and this might be another indication of bursty star formation histories, okay? We didn't see a lot of dependence on stellar mass or a lot of evolution of this relative scatter with redshift. I think this is a really powerful comparison that we can make with simulations, but it might also be direct evidence for this fluctuation in star formation histories, the bursty star formation histories that have been discussed so much in the context of why do we see so many bright galaxies at early times. So and this is a spectroscopic angle of trying to consider this question. Okay, so that's great. Scaling relations, they're super important. If we can measure them robustly, we can get some nice comparisons and constraints on galaxy formation simulations. We need larger samples, we need more representative spectroscopic samples, test feedback models, blah, blah, blah. Okay, yeah, great, okay. But that's not what I wanted to talk about, okay? So actually, I think what I want to talk about is the fact that we keep pinching ourselves, okay? Because with NERSPEC on JWST, we were able to do studies beyond redshift 4 back into cosmic dawn that were not possible at cosmic noon, okay? Redshift 2 to 3, we've been collecting Keck spectra as well as we can for the last decade at plus, and now all the stuff we're doing is rendered completely obsolete by these ridiculous studies that you can do as I'll show you at redshift 9, okay? So what I want to use my remaining time to talk about is just all the wonderfully spectacular stuff that you can do with NERSPEC, and how we should really rise to the occasion because the data are really calling us to do our best job in interpreting them. Okay, so I'm going to talk about trying to get better metallicities based on what we call direct auroral lines and direct metallicities to calibrate our metallicities. I want to talk about moving beyond oxygen abundance. I want to talk about densities. I want to pose a puzzle to people who are doing theories of galaxy formation. I want to talk about dust, and then I want to close, hopefully I'll have time, to talk about something really exciting that I'm hoping to finish my paper on in a few weeks. Okay, so in cycle 1, there were actually 3 programs that were given time to try to establish the calibration between direct metallicity and strong lines. So we could basically apply robust translations between the emission line measurements that are easy to make for basically any galaxy and the physical quantity oxygen abundance. But even before we got our time on these proprietary programs, the public data from the Sears survey turned out to be wonderful for trying to make these calibrations of strong emission lines. So I keep pressing the arrow. Okay, here's the light. Okay, the strong emission line ratios like O3 to H beta, O2 to H beta, R23, O32. This is a neon and oxygen one, and the oxygen abundance. And so this is work from Ryan Sanders using the Sears data set. So basically saying if you make this empirical measurement, you can translate it to a physical oxygen abundance. There's also a nice paper by Lassard et al. Based on the JADE survey. So that's great. There's an issue, which is that this calibration doesn't extend over a very wide range in metallicity. So if your galaxy happens to be here or here, you know, this calibration is not valid. In the Aurora survey, so that's our cycle 1 program, we were able to get direct metallicities for 50 galaxies out of the 100 galaxies that we targeted. And so what are we looking at here? So in each one of these panels, the strong line is the H gamma, hydrogen recombination line, and then this little blob next to it is O3 4363. Okay, so this is now sort of a straightforward measurement to make, and it was really just beyond the capability of Keck really to do this beyond redshift 1, and now you can do this, you know, out to redshift 9.5. Okay, so this is really exciting. I'd say, so my comment on this is that I think the early mass metallicity relationships that have been done so far with NERSPEC on JWST, they're great, but we're just going to redo them once we have these calibrations. Okay, so because we'll be able to calibrate oxygen abundances using high redshift galaxies rather than having to use local calibrations. Okay, oxygen abundance, terrific, but the thing that's amazing is that you can now not only look at oxygen abundance, but you can look at nitrogen to oxygen, carbon to oxygen, argon to oxygen, which it turns out is kind of almost like an alpha abundance indicator. And this is a really nice paper by Kurti et al. Doing abundance ratios at redshift 9.4. And we also know that these abundance patterns have been investigated in GNZ11 at redshift 10.6. Okay, so this is just truly spectacular. So this is just showing some of these abundance ratio diagrams. So abundance ratio versus oxygen abundance from Kurti et al. At redshift 9.4. And mind you, this also has the detection of the 4363 line, so you can really get the direct oxygen abundance at redshift 9.4. So this is wonderful. Something else that I'm really excited about. Yeah, I see. Something else that I'm really excited about is helium, okay? So it turns out that the helium lines are everywhere in everyone's spectra, okay? And previously, I think there was one paper by Kate Whitaker in 2014 that had one helium line, okay? But now you can routinely detect helium lines. So there was a really nice paper by Yanagasawa et al. Looking at the helium abundance in redshift 6 galaxies, and showing, so why is this interesting? It's interesting because it actually tells you something about where the helium is coming from. So the helium abundance is high, and so maybe it's coming from sort of not just, you know, regular enrichment processes. They talk about tidal disruption events, supermassive stars, Wolf-Rayet star enrichment from the CNO process. So this is interesting, but it turns out there's also a degeneracy between the helium abundance ratio, the helium to hydrogen, and also the electron density. But it also turns out that you can break this degeneracy if you detect this near-infrared helium line at 1.08 microns. And guess what? We detect that all the time at redshifts 2 to 3. That was actually showing up in that spectrum that I showed you at the beginning. So this is a helium line. So we can actually make this measurement robustly. And in the Aurora survey, our program, for example, this is a galaxy at redshift 4.4, where we detect 8 lines from helium-1. Okay, and so we can robustly look at the helium abundance, which is, again, this is the type of analysis which people do in local H2 regions, and it was just beyond the reach of high redshift galaxy studies. And so it opens up a whole new window in studying the way the galaxies are assembled in terms of their chemical enrichment patterns. Okay. Okay, this is the puzzle. This is one of the puzzles. Why is the density so high? Okay, so now Dan was talking about, did you talk about this? I don't know. Did you mention the high density? So, okay. Well, anyway, one of the things that's come up a lot in GNZ11 is that the density is really high, and also in the Michael Topping's paper about have really high density. Okay, but more globally, you can see an evolution in electron density from the local universe, you know, back in time. Okay, so we're going back to, this is a compilation in Michael Topping's upcoming paper, where you can see that the density is evolving. You say, okay, well, that's just because the galaxy properties are evolving. But what's really interesting is if you look at any given redshift, so this is Michael's compiling the galaxies in our different redshift bins. There's no correlation between the density and any galaxy property. Okay, so the question is, why is the density higher in these early galaxies? And that's, okay, people modeling the galaxies, this is a really interesting question because it seems to be an observation that actually we've been building up for the last 15 years. We already were finding that the densities were high in redshift 2 galaxies, and now it seems to be sort of a pattern that is continuing to earlier times. Okay? All right, so I got sort of like 2 more topics. Okay, so that's fine. I think I'm doing, yeah. No, it's okay. They're short. So the other thing that's really important, and this is what I'm saying about the spectra are so great that it behooves us to try to do better. Okay, so now this galaxy at redshift 4.4. Ryan Sanders just posted a paper about this. Ryan was able to measure the dust attenuation curve in this galaxy based on 11 hydrogen recombination lines, 8 Balmer lines and 3 Paschen lines. And the curve does not look like the Cardelli law, okay? So all you people just measuring H alpha to H beta and saying you've measured the dust attenuation, that's not the case for this galaxy, okay? And this is actually, we talk about H alpha being the gold standard of star formation, but that's only true if you can actually do a good dust correction. Okay, so what's really exciting is that in data, you know, this is not the only spectrum for which we measure multiple hydrogen recombination lines. In the Aurora sample alone, we have 25 galaxies where we can construct the dust attenuation curve on an individual galaxy basis and determine the systematic variation of this dust attenuation law in high redshift star-forming galaxies. Okay, so again, this is a big systematic in trying to construct the main sequence of star formation, and now we can actually hopefully eliminate the systematic uncertainty by measuring the dust curve in individual galaxies. Okay? All right, so the last thing that I want to talk about is something that just came up in our data that was totally unexpected, and I had a cute little acronym several months ago, but I still haven't finished my paper, so I thought it might be a little bit old. But I wanted to call this is a big metal-rich disk, so a BMD. We've heard so much about little red dots. This is something, everything needs an acronym. And this is my last little anecdote. So let me just tell this really quickly. Okay, so this is a galaxy. Actually, it was a known dropout from HST work. What was not known was, first of all, that this thing is large. It's at redshift 6.73. It has an effective radius, Erica, you'll be interested in this, of about 1.5 kiloparsecs, okay? Compared to the typical sizes of galaxies at this redshift of about 0.3 kiloparsecs. It's massive. It has a stellar mass of 10 to the 10 solar masses. Okay, I did it using an old-fashioned code, but if you use Prospector, it's even higher. It's a little more than 10 to the 10 solar masses. Okay, it's also red. Okay, it has a beta. Dan was just telling us about beta of -3. This thing has a beta of 0.5 at redshift 7. Okay, so I know that this typical storyline of redshift 7 galaxies is the very blue, low metallicity, but this thing has a beta of 0.5 at redshift 7. Okay, but that's not the best part. The best part, of course, is the spectrum. Okay, so this thing at redshift 6.73 has a detection of more than 15 of these emission lines. And what does it tell us? You should already, spectral experts should already be surprised that there's nitrogen, okay? So we heard a lot about, like in the little red dots, like maybe they don't have that much nitrogen, maybe they're metal poor AGNs, but not this thing, okay? So if you put it on various emission line diagrams, like this is an N2 BPT diagram, the orange point in each one of these diagrams is our redshift 7 galaxy, our BMD. It sits here, right where these red points are from the Aurora and Mostev surveys. You can see it just looks like a redshift 2 galaxy. This plot, I just want to say, this is an O1 BPT diagram that has 50 points on it beyond, redshift 2. This diagram like didn't exist for high redshift before, and now with JWST it's routine. This is an excitation. These are a couple of excitation diagrams again. You can see this thing sits where the redshift 2 and 3 galaxies are, but it's at redshift 7. And also it looks like it's already pretty enriched, okay? So it looks like it's basically at least half solar metallicity at redshift 7. Okay, so how did this thing get made? And that's a really big, interesting puzzle. It's large, it's massive, it's metal rich, and it's dusty, and it's at redshift 7. Okay, so this is we need to understand not just the sort of typical galaxies at redshift 7, but also the extremes. Okay, so this is sort of a political talk again. We're in an election year. I think there are lots of really interesting things we can do with JWST. I think we're loving the Aurora survey so much, but it's small. It's only 100 galaxies. I think that a wonderful legacy for JWST will be to construct a much larger sample of these beautiful spectra because it's easy to get them, and we can learn just so much from them. So I'll stop. Thanks.
Thank you, Annalise. Can I ask someone to help with the microphones, please? So we have only 4 minutes for discussion. So Joe.
Thanks for the very high energy talk, Alex.
You're going to give me a quiz. You're going to give me a test, right? Okay.
So since you mentioned BMDs and LRDs, I noticed if you could go back that there seemed to be a broad H alpha base to that line.
Oh yes, very well spotted, Joe. Very well spotted. Yeah. So yes, right. This is not well fit by a single Gaussian. So yeah. So what I'd say is that you want to say, is it an AGN?
I wasn't putting words in your mouth, but.
Yeah, so the issue is that I'd say we don't yet have enough information to say conclusively what the model is. So you can model this as you can decompose the line into like an unresolved component and then like a broad component that has a full with half max of like 300 or 400 kilometers per second. You could decompose it into like something where most of the light is in a component with like a full with half max of like 350 kilometers per second, and there's just a very low level broad H alpha. So actually, I think what we really need to do is use the NIRSpec IFU to map the galaxy because it has a really interesting structure. I sort of glossed over this. But you can see, this is like a low light situation, which we don't have right now. But what you can see is that there's sort of an extended light distribution, and then there's just like this blue dot there.
Great. So I'm impressed with your conservatism and fastidiousness in fitting the broad base of that line. Can you, not everybody's that conservative, can you comment on the helium-2 lines? Because I saw that in the object where you showed all the helium lines. So what's the source of the 54 Rydberg photons? Because a lot of folks would also say that that's an AGN phenomenon.
This thing here?
No, the one before, there was helium-2 Balmer, right? Helium-2 4686. That's definitely there.
Where did I?
In the top panel.
Oh.
Yeah.
Yeah. These are. Well, this is not mine. I mean, so this is a.
Oh.
Yeah. One of the models I think for understanding this galaxy is that there might be like really massive stars with hard ionizing spectra.
Got it. Thanks.
4686 is detected in like Wolf-Rayet galaxies.
Yeah, so but
right?
that
so
doesn't.
Massive stars.
That was part of your beautiful PhD thesis, but that had a P Cygni profile, which this one doesn't.
We should move on and ask and let Crystal to ask the question. Thank you.
So looking at those same broad wings, I note that on the O3, the wings looked awfully similar to the H beta wings to me, which would make this very unlike the type 1 AGN. But that's not the question I wanted to ask.
No,
which
actually,
is about,
no. Sorry, I have to say, no. I have to say, this O3 5007, it's not a broad wing. It's actually, there's a helium-1 line at 5017. The data are good enough.
But the 4960 looks just like the H beta.
Yeah. Well, that one actually is well fit by a single.
But the question I wanted to ask is about your beautiful Balmer series and all those lines and getting dust. And I'm curious, when you use different Balmer ratios to get the dust, often one has to account for stellar absorption to get consistent values between different Balmer ratios. And I'm just thinking that stellar absorption will be very sensitive to, A and F stars, older stars, and the star formation histories.
Sure.
So I'm curious if you've found anything interesting there or looked at that.
Yeah. Well, this galaxy is really young. So, I mean, the thing is, for the underlying continuum, we used our SED fit model. So that automatically takes into account the stellar absorption. But this thing has a best fit age of, like 10 million years. So the underlying stellar absorption is not too strong. So, but of course, yes, we always, when we were measuring the Balmer lines, we're always taking into account the underlying stellar absorption from the stellar population model.
Okay, so let's thank Alice
Oh,
again.
okay. So,